How's the day?
Very busy, to be honest. I don't know why, but a very messy day.
Sorry for that. Well, some days are like that. That's cool.
Yeah.
Yeah. Okay, so I think basically we say we're going to begin the earthquake loading and everything today.
hmm
Okay, so first of all, share your screen, but we might not do more of design today because first of all, I'll need to explain to you about earthquake and also EuroCode 8. But just share
Yeah.
your screen first. Let me see your screen.
Okay. Uh, so, do you want me to open the Prota?
Yes. Open the software. Yeah.
Okay. Meanwhile, I have taken some time to study some features regarding the structural frame, so that the position of the columns,
Okay.
how they are orientated, um, regarding the first three modes of the natural period.
Okay. That's fine.
So
That's nice.
something like more theoretical, but based on Eurocode date, so that I can make even your work, let's say, simpler.
Okay. Yeah. That's fine. That's good. Okay.
The concept of that Eurocode says a lot about the strong column and weak beam, how is it done, or how it is controlled. I
Yes.
took some I took some notes from a book that I have regarding the preliminary design, because, as you may know, I'm a new designer and I don't have your experience, let's say, regarding the dimensioning of the column, the pre-dimension, because normally they change.
Okay. Yeah. That's true.
I took some notes about the preliminary design. So, for the type of the slabs, for the beams and things like that, for the columns, this was very difficult regarding the Eurocode date
Okay.
to have a preliminary design. So you should have, let's say, a prediction regarding the loads before you can take some pre-dimensions.
Yeah. Sure. Okay. Then also,
And that's all.
okay. I heard that I think over the news that there was earthquake on Monday in your country, although not a major one, but just a minor earthquake. Is that true?
Yeah, yeah. Very weak one. Quite. We didn't hear it.
Okay. 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 So just open a project. Open a project first. Let me see.
The new project,
No. Open that shopping project. Yeah, it's that one. Open the
shopping
shop.
plaza.
Yes,
Okay.
open that one. Okay. Coming.
Yeah. I have seen even some videos in your channel regarding the type of software that you have done for the detailing. I think that later on you will explain me that, because it was interesting.
Okay. Okay. Yeah. Okay. That's fine. So let me see. Okay. Yeah. That's good. So now, basically, before we must begin earthquake, because
hmm
basically this software does, let me say, like 80% of the work automatic for you, although you will still have to key in those values before it can do it for you. But
hmm
for you to be able to understand what the software is doing, I think you need to get at least basic principles about earthquake in regards to EC8. That's EuroCode 8.
Yep.
Okay. So then, right now, I will say that when we talk about earthquake, or let me say, when we talk about seismic design, there is two things we have to put into consideration. First of all, is one, um, we have to consider one, ductility, and two, energy capacity, or let me say energy dissipation capacity. So these two things is what we are going to consider, because these two things looks very um it looks like a small word, but they are very deep, because when you enter into these words, you now begin to see that almost everything about seismic design and also earthquake falls into these two words, majorly ductility. Okay,
Mm-hmm.
then therefore, in that now, I will say that ductility in terms of structure is the capacity of a structure to enter into elastic range without any form of collapse. But before then, there is something I will have to say, and that is, when you're designing for an earthquake, or yeah, for an earthquake structure, or for any building around earthquake zone, there's something you must carry in mind. You are not designing the building to at least resist the earthquake entirely, but you are designing that structure to be able, whenever, if there is a minor shaking or minor earthquake, let me say minor, moderate, or major earthquake, it will not have great damage, or let me say great impact, that will lead to loss of life, loss of property, and then also loss of costs, let me say in terms of let me say economy and all that. So note that
Mm-hmm.
when you're designing for an earthquake structure, you must carry in mind that if there is a major earthquake, like a major earthquake, or let me say moderate earthquake, that building can have a slight crack, but not that it will collapse immediately, or not that it will collapse, but it might have a slight cracks, which will not affect which will not affect human lives, property, and all that within that time range of that earthquake. Then after that earthquake, there is also another design that you are meant to done that sorry that you are meant to do to now repair those cracks, or those impacts. And then I think EuroCode 8 also have that kind of code, because EuroCode 8 is being divided into 6 parts. Hope you know that. We have part one,
Yeah.
part two, part three, part four, up to part six. We have in EuroCode 8. Okay, so again, I come back to what I was saying before about ductility, which is the capacity of a structure
Mm-hmm.
to enter into elastic range without any collapse. Now, since we are focusing first on reinforced concrete, because how you design for a seismic design for a reinforced concrete is different from how you design for like for a steel structure, and also it's different from how you design for a bridge. So we are first of all focusing on reinforced concrete, which is building.
Mm-hmm.
Now, a reinforced concrete section, how to make a reinforced concrete section ductile. The first thing that you have to do to make a reinforced concrete section ductile is just two things. One, either you have to reduce the load of the compression zone. Then the second one, either you have to increase the strength of the ultimate deformation of the compression zone. Now I will first of all go to the first one, which is to reduce the load of the compression zone. When we talk about reducing the load of the compression zone, we talk about limiting we talk about limiting the axial force in the section, or we talk about using the compression reinforcement, or we talk about limiting the ratio of the tension reinforcement. Now, this first one is not mostly considered, because you cannot have, let me say, a 10-story building, and then because that structure is to be built in an earthquake zone, you will not want to go and reduce the weight of the structure, of which that that structure itself has its own self weight. So there is no way you can reduce the weight of the structure totally to now avoid um seismic,
Loss of
yes,
ductility.
effect. So the only way to do that is to use the second option, which is to increase the strength of sorry, which is to increase the strength and ultimate deformation. So when I talk about increasing the strength, simply means either you increase this like the size of the concrete section, or you increase the size of your reinforcement. And also, increasing the strength also comes into play when it comes to detailing, like for you to detail a joint between a column and a beam. Those things also talks about strength. Now, for the strength, which is for that second option, which I said, increasing the capacity of the compression zone, three things must come into play in that area. First of all, you have to choose the section of like you have to choose a good section that that is okay for the structure, which is the section of the members, either the column, the shear wall, the beams, the slab, and all that. Then two, you have to use a high class grade of concrete. That's another one again, inside that, increasing the capacity of the compression zone. Then also you have to use a strong confinement. Now, when I mean by confinement, it might look a little bit confusing, but when you're designing for an earthquake, like when you're designing for a structure against earthquake, you must deal with confinement. Confinement, let me just use a typical example of what they call confinement. You know that for any seismic design, or yeah, seismic design, you must tie your columns on the ground with a ground beam, so that it can form, like it can be able to transfer load evenly. I don't know if you know what I mean, by using a ground
Yeah,
beam around the column. Yeah. So that beam now under that column is serving as a confinement. So when you're designing for that beam, you have to design it very well as a confinement element, or let me say member, because
you are
if
telling practically to respect, let's say, the critical zone in column, let's say, but even the beam has critical zones.
yes, exactly. So they using strong confinement on that. So that is for this increasing of capacity and all that. Then there are factors contributing confinement. When you talk about confinement, there are some factors you are meant to consider, and those factors, one is the link and bar spacing, either for the beam or anything. You must consider the link and bar spacing. You must consider the link and bar diameter. You must consider the link and bar steel grade strength or steel strength. And then you must also consider the arrangement of the vertical bars. That's for the columns. You must consider the arrangement of the vertical bars. And then you must consider the shapes of the links for the beam or for the column. Because the shapes, if you don't use a right shape, it will also affect the strength of that member. Then there is also the last one, which is not mostly used, which is mechanical way, like let me say mechanical way of you like doing the hoops like a link, but that one is not mainly used. But the first five, which I said, which is the link spacing, the link bar diameter, the link and bar steel strength, the shape of the link, and the arrangement of the vertical bars. These ones is the major ones when you're like the factors that contribute to a stronger confinement. Then also, when we talk about earthquake design or seismic design, we also talk about capacity design, and what makes and the goal for a capacity design is to protect the important elements like columns and non-ductile elements. So when you're designing for a seismic design, you have to consider capacity design by protecting the those first of all columns, which is the main element, and then non-ductile elements like beams and I think beams, yeah, and most times shear wall. But although shear wall is being considered as a ductile element, but most people still consider it most times as non-ductile elements. Then now, regardless of the intensity of the earthquake, the force of non-ductile elements or that the force of non-ductile elements must not be more than the one of the total elements. So what I mean is that regarding the intensity of the earthquake or what you're designing, let the force, like the beam, let me say if you're using a diameter bar of 20 for your beams, you must not use a less diameter bar for like columns. So now let me say like for the strength for the total element like columns must be higher or equal to the non-total elements. I don't know if you get what I mean there.
Yeah,
Okay,
yeah, understand. So
okay. So this comes into play when you're doing your let me I think when you're doing your let me say
detailing.
yes, detailing. Then also let me just use this medium to explain about the joint between the column and the beam. If maybe you are using a link spacing of 200 for your or let me say 175 millimeter for your columns, when you come to the beam, the I think the joint between the beam and the column for like for some percentage on the beam, you have to use you have to use the same spacing you use for the column on the beam area, but not throughout the beam, but to some certain percentage. I don't know if you get what I
Okay.
mean.
Yeah, yeah,
Yes, because that will form a good connection between the beam and the column, and also when there is let me say when there is a shake or let me say vibration, it will help a lot because if you use a different spacing on the beam joint between the beam and the column, and then you use a different spacing on the column, when there is let me say vibration, you will see that either the beam will have to fail that joint between the beam will like fail. It will either cause what they call drift, either I think it will either cause what they call upward like sorry uplift. Yes, it will cause uplift because that joint is not firmly like it's not strong that much, or it's not firmly I think like let me say it's not firmly in like in connection with the column. So always use the same link you like use for the column, also for the beam, but not to some certain percentage. Okay, then we now go to what they call sliding shears. And EuroCode, when it comes to sliding shears, I think EuroCode was the first to like introduce what they call bi-diagonal reinforcement. When it comes to sliding shear, over the years, most of the buildings, even if they were able to withstand that effect from like from the earthquake, they will see that most of the members will like fail in this like in sharing. So when this code came into existence, EuroCode, they now introduced what they call bi-diagonal reinforcement for ductility class high. You know, when it comes to ductility or earthquake, the first thing you consider, either you consider ductility class high or ductility class medium, which is DCH and DCM. So these two,
yeah,
although you will still see it on this software when you're going to do that. What influence this DCH and DCN is the what they call behavioral factor, which is Q. I think, yeah,
Q.
behavioral factor, yeah,
Yeah, I
Q.
know.
So I'll also show you that later. But first of all, for the sliding shear, EC8 introduced what they call bi-diagonal reinforcement, which takes care of the which controls uplift. So I think bi-diagonal reinforcement is like an X, like if you're like an X along the beam, you have to cross and like cross diagonal reinforcement along the beam. So that bar now is called a bi-diagonal reinforcement, and this bi-diagonal reinforcement is being found one in a beam, two in a squat wall, and three around the coupling beams in a wall. So this is where you can introduce this bi-diagonal reinforcement. Also, bi-diagonal reinforcement is very useful for shear resistance since because it was seen that normal steel ropes, like normal link that we use, which is just normal conventional link that we use for beams, is like when it comes to earthquake, those links are just like they are not useful. But if you introduce if you introduce bi-diagonal reinforcement, you will see that it will be able to control anything like uplift or shear or like shear failure, or let me say, yeah, shear failure in that
This is only for the high ductility structures.
what do you say?
This bi-diagonal reinforcement is done only on high ductility structures.
No, yes, only on high ductility. Yeah, most of the times we use high DCH. That's the high ductility class. That's what we use mostly for design. But except maybe in some countries which does not have major or moderate earthquake, then you can now begin to use the
Do you have any example in detailing which you can share with me with this bi-diagonal reinforcement? Because I don't think I have seen it, or it's just another term in here.
Okay, let me just make a sketch and then snap for you on your WhatsApp for you to see.
Okay.
Okay. Then also, okay, I think that's fine. Let me just make a sketch first and then show you that. Then I think I'm almost done. Okay. Then when it comes to, okay, let me just snap first and then make a sketch for you that. Um, okay, coming. Okay. I think take your WhatsApp. Let me just see your WhatsApp now. Coming. Yeah, check your WhatsApp now. I think I've sent it. It's coming.
Yes.
So have you seen that?
Ah. Yeah.
Yes. So that is what they call bi-diagonal reinforcements. So you have to put it in some
Mm-hmm.
critical areas of the beam, not everywhere on the beam, but some critical areas, mostly around the joint, which will occur, which anywhere you feel that the uplift will like occur, you put it in that area because uplift occurs mostly around the joints. That's where uplift occurs. So that's where you have to put it.
But this six is formed, let's say, by joining two like Z
No, X.
rebars, right?
It's like an X.
Ah, it's
X.
simple X.
Yes. Simple X. It's simple X.
This X is done on the sides or throughout the width of the beam.
Not through out of the beam, around the joints. You have to,
Ah, around the
yes,
joints.
around the joint because
Ah,
this particular reinforcement
they
only,
brace the joints, let's say.
what do you say, joint between the column and the beam or joint between the wall and the beam,
Yeah.
you put this.
So they brace the stirrups on the critical zone, let's say.
Exactly, with this diagonal reinforcement. Yes.
And this is done on the fourth sides of the beam, let's say.
Yes, on the sides of the beam.
Okay, I got it.
Okay, okay. Then I think we now move into basic design steps. I think it's just what we did before. Basic design steps simply means there are 4 steps to consider first. The first thing to do is the conceptual design, which I think which is just this one that we just modeled here, which we have to take care
Mhm.
of the static load and all that. Then now determination of the behavioral factor, which is the Q. That one is very, very essential. You have to consider that too. Then the capacity design, which I told you before, capacity design,
Mhm.
which the goal is to protect, the important elements like columns and non-ductile elements like shear walls and beams and all that. So that is the capacity design. So you have to choose adequate size for the column, adequate size for the beam, adequate size for the shear wall. Then the last one, which I told you last week, I'm sorry, on Monday, about the detailing. Detailing is very, very important. Like, in fact, it is the most essential. This number 4 is very important, which is the detailing, because if you do a good design and a very poor detailing, that means that even the design is just like, let me say is not useful. So you must make sure you detail very well. And most times there are some things you have to apply in your detailing, like this bidiagonal reinforcement. You might not see it in the design, but it is essential for you to apply it in your detailing. So that's why I say detailing,
Mhm.
there are some things you might not see in the design, but during your detailing, you have to put them into consideration. Okay,
Okay.
that's fine. Then the other one,
So
I've already,
the
okay, let me hear you.
as a summary, so it's very important to the ductility, the capacity design, the detailing, and the behavior factor. So these are, let's say, the main issues when you tend to design a seismic structure. Let's say.
Exactly. These 4 steps is the main thing, is main design steps that you have to take. Which the first one is this
Mhm.
one that we have just modeled now. And the second one is the dimension of the behavioral factor, which you get from the code there. Then this third one is the capacity design, which is your column, yes, the beams and all that, to make sure that the column, like to protect the column from failing, because column is the principal element or a principal member. Then the last one, detailing. Okay.
Yeah. Okay.
Then right now, I think I was studying your country, that was earlier this week, about earthquake, and I saw that your country, I think, like is the highest, like is the country that experienced more earthquake around your region. I think European nation. I don't know if that's true.
Yeah, for number of earthquakes, yes. For the intensity, I think
No.
Greece is the
Yes,
highest in
Greece.
Europe.
Yeah, I think what I saw was that you guys experience earthquake most often, but not a major earthquake. Major earthquake can come in
Yeah,
like 10 years time
our
or 15 years time and all
our
that.
highest earthquake were,
It's just a minor,
yeah, yeah.
or
We have
yeah,
a period of 50,
yes,
50 to
yes,
70. Yes, that's the period
exactly.
time of return.
Okay.
Our last biggest earthquake you can see on your free time was on 2019 on November.
Yes, exactly. That was a major earthquake. 2019 was a major
That
earthquake.
was a major earthquake. It, it,
Yes,
it was quite
I think they're about, I think 6.5
7
or
point six point
7.5
four.
or so, yeah, magnitude. I saw that.
Yeah.
Yeah, I saw that.
50 people died, and a lot of structures near the seaside were destroyed. In Tirana, where I live, which is the capital,
Yes, I saw that
they
too.
were collapsed two or three flats like residential buildings, but they were old communist buildings. They were not new buildings.
Okay, yeah.
Meanwhile, on the seaside, were all the structures destroyed, and basically all the people who passed away were from the part of the seaside.
Yeah, like your like a region like Leshi, I think Leshi. I don't know Leshi in your country. I don't know if you have that.
Mm.
Lezhe, Leshi, I think so.
Yeah.
Yes, that place was majorly affected too. Okay.
Yeah.
Then I was also seeing in your country, you guys have a code that's called KTP 89. That's your seismic code, right?
Yeah, that's our seismic code. It's from the 1981.
Yes, but I saw that that code has some issues because it doesn't
Yes, it's
consider,
very old.
yes, it doesn't consider soil factor. It doesn't consider soil
Yes,
factor. Yeah, and that's a major issue.
because yeah, it's done on 1981, so it's very old and quite anyone uses it.
Okay, okay, okay,
We are based on EuroCode. Most of the designers tend to use the annex of Italy because that of Greece is very conservative.
okay. Yes, that's
Do you
true.
know the annexes of EuroCodes? They have different
Yes,
coefficients
yes,
of it.
Anes, yeah,
The
different
Greece one
countries.
is very high, so that yeah, it is. No, I think that we are more near to Greece as numbers as of Italy, but they take the Italy numbers because of the economy. You know that higher coefficients cost a lot in construction. So
Yeah, okay. Then also, I think, then, okay, let me now enter into the Eurocode majorly. Eurocode. Then, first of all, okay, I think we to explain this more because I'm done with the basic explanation. Then, what is left now
Mhm.
is the detailed explanation, which comes with formula, and by doing that, we will have to begin to load the structure in terms of earthquake, so that I can now begin to explain each of those tabs for you.
Yeah.
Right, okay. So right now, let's go and add earthquake load to this structure.